So good morning, everyone. First of all, I would like to thank the organizers for giving me this opportunity to talk in this wonderful conference. And I'm Ingita. I'm from Griffith University, a PhD student. And today I'm going to talk about something that you might not have heard before, something called counterfactual quantum trajectories. I know that quantum trajectories you have heard many a times before in this conference. Okay. So to start off with, let's try and understand what counterfactuals are. So in our everyday life, we find ourselves wondering questions like, what if we had done something else? What would have happened if we had taken a different decision? And these are some typical examples of counterfactuals. For instance, what if we stopped emitting greenhouse gases? Now, you might wonder why counterfactuals? Well, counterfactuals play a very important role in understanding the modeling of the world and what are the effects of our actions. It also has a very important role in decision making and game theory. Also, counterfactuals play a very important role in understanding causal relationship between events. For instance, this is a very good pictorial depiction by Julia Pearl, where he shows 3 levels of sophisticated questions that you need to answer in order to understand the causal relationship, cause and effect relationship between events, where counterfactuals are the highest level of the questions. Well, I'm not going to talk about causation in this. What I'm going to talk about in the next couple of slides is how do we apply counterfactuals. There are various approaches in which we can evaluate counterfactuals, and we follow a particular approach given by David Lewis. So David Lewis was a philosopher in Princeton University, and he had his analysis of counterfactuals based on something called similarity analysis of possible worlds. So a counterfactual question has 2 parts. The first part is the antecedent, the thing that you propose to change, and the second part is the consequent, the effect of that change that you implement. And when Lewis said that it's a similarity of the possible worlds, what he meant by this is that when you want to ask a counterfactual question, you want minimal deviation from what actually has happened in your world. So except for the thing that really needs to be changed, or you want to keep the rest of the things as it was in the actual world. And we try to use Lewis's approach of evaluating counterfactuals, which gives us a motivation and to ask a question like, can we apply counterfactuals in quantum theory? Or more specifically, to quantum trajectories. However, counterfactuals face challenges in quantum theory. Let's see what are these challenges. So Lewis, in his analysis, assumes classical laws when he talks about evaluating counterfactuals. However, quantum theory is very different from classical theory, and therefore, how do we try to resolve this problem is, we try to restrict our description on using the classical elements of the theory. That means when we are going to talk about our counterfactual, we'll only talk about the measurement settings, the measurement outcomes, and the states of the knowledge of the observers. And the second problem is that Lewis also assumed deterministic laws, which is the classical laws. That means when he proposes a counterfactual question, the counterfactual question always has a definite truth value with unit probability. Whereas in quantum theory, you don't have a definite answer to your question. And therefore, we assign probabilities to different possible counterfactual propositions. Now, having resolved some of the problems that counterfactuals will face in quantum theory, we move on to, and let's see how we apply them. So Lewis said that we need to keep certain points in consideration while framing a counterfactual question. The first point is that we do not want to violate any laws of the theory where we ask our counterfactual in. And from that first point, when we ask our counterfactual question, what we propose to change, which is the antecedent of our counterfactual, is the choice of the measurement settings. So we have an observer who is observing a system, and we are saying that if that observer wants to use a different measurement setting. And because it's a free choice, it does not violate any laws of quantum mechanics. And the second point is based on the similarity of possible worlds, where he says that we need to maximize the spatio-temporal region throughout which perfect match of a particular fact prevails. So what this essentially means is that if you have an event, let's say A, and you want to change this event and want to see what is the effect as a result of changing this event, everything that will be outside the future, so this is a future light cone, and everything that will be outside the future light cone of that event needs to be kept fixed while we evaluate our counterfactual. So if we have any observer, any other observer observing or measuring, making measurements on the same systems, we have to keep the other observers' outcomes and measurement settings fixed. Okay, so let's try and understand the application of the counterfactuals from a very simplistic bell-type experiment, where we have a singlet state, and the singlet state is being shared between Alice and Bob. Alice actually, in the actual world, she has made a measurement. She had made a measurement along the Z component of the spin, and she's trying to ask a question that what would have happened if she had measured the X component instead? And the question here is, can she estimate and get more information using what she actually has measured, compared to if she does not use her actual measurement records? And if in this entire scenario, Bob's measurement outcomes and records need to be kept fixed. So here is a singlet state. Alice's actual measurement choice is a Z basis, and she gets an outcome spin up, which collapses Bob's state to spin down. Now, Bob's measurement choice is the standard measurement choice in CHSL type experiments. This is known to Alice, but Alice does not know Bob's possible outcomes. So she can write down the possible probabilities of Bob's outcomes. And then, because she has to use this information and keep it fixed while she asks a counterfactual question. Now, in the counterfactual scenario where she decides to measure the X component of the spin, she uses this information, and now she has to calculate a probability, which is the counterfactual probability. That is, what is the probability of the outcome of the X, given that she had actually measured the Z component and got a spin up. And this will be the sum over all the possible outcomes of Bob, which stays fixed in the counterfactual scenario as well. And turns out, when she does this, she actually gains some information, some more amount of information compared to if she was not using her actual measurement records. Now, we try and apply this in the continuous monitoring scenario. In here, we have, again, two observers, Alice and Bob. We have this two-level atom, which is interacting with two cavity modes and being resonantly driven along the x-axis. So essentially, the state will also always be confined in the YZ circle of the log sphere. And what Alice is doing is actual measurement outcomes are capital N, and Bob's actual measurement outcomes are capital M, and both of them are actually doing photon detections. So that's what they have actually done. So Alice had made a photon detections and has a sequence of records. Bob has done a photon detections, has a sequence of records, but Alice does not know Bob's outcomes. Now Alice wonders, okay, given that I have done these photon detections, what would have happened if I was doing, or like what would have happened if I was doing homodyne detection, which is a different type of a detection instead? And Alice here has just 20% efficiency of the measurement, and the rest of the efficiency goes to Bob. So this is basically the true state as in the state which is conditioned on all possible measurement outcomes of Bob as well as Alice, so it's always pure. All right, so let's see how do we frame the counterfactual question in quantum trajectories. So as I said that Alice had actually used a photodetector and seen a particular sequence of jumps, and then she asked the questions that what would she have seen if she had chosen to measure the fluorescence using homodyne detection? Well, a single homodyne record looks very noisy, and it's not possible to keep track of all of them. Therefore, what we look instead at is all the trajectories of the atom conditioned on those records and look at the average over them. All right, so this is what actually Alice has done. So Alice has a sequence of photon detections where she just records one click in her detector in the entire monitoring time. Because she does not have full efficiency, so it goes up and starts equilibrating. When she detects a photon, the atom goes to the ground state and starts the Rabi oscillations again. So this is what we call the filtered state because it's conditioned only on what Alice has seen in the past. And this notation is very important because I'm going to use it in the next couple of slides where this state is only conditioned on Alice's outcomes. So it's basic, and capital M was Bob's photon detections. And so what this essentially means is an ensemble of average over Bob's outcomes conditioned on Alice's outcomes. Okay. So now smoothing is a technique which gives you better information, and Howard has talked about this before, quantum state smoothing. So we'll use the calculation similar to smoothing technique in order to get a better estimation. So Alice now tries to estimate the smooth state for a single jump. So as you can see, it's the same thing, but now conditioned on past future records of Alice. So the smooth state here, because it also has information from the future records, it knows that around this point a jump is going to happen, and therefore it tries to weigh the excited state more as compared to the ground state, and that's why it's more pure around the region of the jump here. Okay, so now Alice moves on to the counterfactual scenario, where now the true state here is conditioned on still Bob's measurement records M, because Bob's records need to be kept fixed, so Bob is still doing photon detections. And now Alice changes her records to Y, which is now a homodyne detection. So initially her record was N, but now she changes her record to Y. And this is a true state of the system. Now she conditions these true states on two conditional probabilities. So the first one is, as you can see, that this is Alice's past future records. She does not have knowledge about what Bob's possible outcomes would be. So she tries to guess an estimate of the distribution of Bob's possible outcomes given her past future records. And then she uses another conditional probability. So now, because Bob's records need to be kept fixed in the counterfactual scenario, she defines another conditional probability that given Bob's records, which are still fixed, what would my homodyne records be, or the possible distributions of the homodyne records. And then she performs an ensemble average over all possible records of Bob and correspondingly all homodyne records to get her final counterfactual state. Now here, this red part here I have highlighted here. So this is like the sum over the Y with this probability and the true state will give you a state which looks like something as if Bob was doing a smoothing calculations in the counterfactual scenario. And what Alice has to do essentially is do an ensemble average over all possible smooth states of Bob. So this is what Alice sees is the ensemble of Bob's possible smooth states. Here is a point where Alice sees a jump. Alice has seen a jump, basically. So essentially, what I've plotted here is just 100 possible trajectories, but if I plot all the trajectories, Bob can see a jump anywhere, except at this point where Alice sees a jump. But the reason I have plotted 100 trajectories is to show a trend of that Alice actually estimates Bob's possible ensembles very nicely. So at the point where Alice has seen a jump, she knows that Bob cannot see a jump exactly at that point. And because the atom goes to the ground state immediately after the jump, she knows that the atom has gone to the ground state, so it slowly starts to repopulate the excited state. So immediately after the jump, Bob will be least likely to see a jump. But then, around half a Rabi cycle later, at this point, where the excited state population has again gone to the maximum, Bob will be most likely to see a jump because the excited state population is maximum. The emission probability is maximum for Bob. So here will be the point where Bob will see most jumps. And the same theory applies half a Rabi cycle before Alice sees jumps. And this trend is actually, so what Alice will do is perform an ensemble average over all of these possible trajectories to get her final counterfactual state. And when she does this, she gets this state, which is her final counterfactual state, this black line here. And as I said, because Bob will get more jumps at this point and this point, what happens is it pulls down this average, ensemble average on either side. So you see these dips here because Bob's ensembles mostly was going to -1 in these points. And because he does not see a jump around this region, it becomes like you have this peak around this point. And when she tries to compare this with what actually she has measured, so her actual smooth state was this red state where she was doing photon detections, but now her counterfactual state is this green state. So what she understands from her actual measurement records is that her counterfactual state will approximately follow the smooth state, roughly follow the smooth state before the jump. And because this smooth trajectory is basically a discrete quantum trajectory, but the counterfactual state is an average of continuous trajectories, which is homodyne records. It does not have this sharp fall here, and it continues beyond the jump. So, which was very counterintuitive, because until the jump, it approximately follows the true state, the smooth state, but after the jump, it kind of becomes anticorrelated. So this is what Alice gains information about her counterfactual state without actually doing the photon detections. Homodyne detection. And this is similarly measuring the Y component of her state, which is just like 90-degree out of phase and has the same story. So with this, I come to the conclusions. So what we try to do here is try to ask a counterfactual question in quantum theory and quantum trajectories, which was not very easy to do. So we tried generalizing Lewis's approach and apply them in quantum theory. We would like to see if there are other ways to answer this question. How does these type of question relate to other models of counterfactual reasoning? And can it give a better understanding of causation? And if you want to know more about this, whether counterfactual gives a better understanding of causation, you can refer to this paper here by Eric and colleagues. And I would like to thank my supervisor, Howard Wiseman, and my co-supervisor, Kian, who is also a former PhD student of Howard, now in CNRS Maju Lab at Singapore. And they have extensively helped me in doing this project and have been very patient all throughout. So with this, I come to the end. And so this is a picture of Howard on the edge of the cliff, coming up with more weird counterfactual questions. Thank you so much for your attention.
So any questions?
And just to be sure that I understand, so in the first part, let's say Alice first had a measurement record of in the Z corresponding to Z measurements.
Yes.
And she had a record of both Alice and Bob. Is it
no? So in this,
or she knows exactly what Bob will.
So she knows Bob's measurement choice, but she does not know what is the exact
she doesn't
outcome.
Have the record. Okay.
She does not have the record. But she knows Bob's measurement choice, so she can guess the probability distribution for Bob's outcomes.
Okay, but she has her record
she
on
has
Z
her own
spin,
record.
and then she wants to, if she had made measurements in the X direction
yes.
or something, then she wants to find out what's the best
yes, what's the best answer
prediction.
To that? Yes, exactly.
But doesn't that go down as with with time? Like if she has a record for some time.
Yes.
I mean, the predicted DA, I would imagine that it should go down as you, at later times, it should be, the prediction should be worse. Is that right?
So this is just with examples of like projective measurements. But then if you go into the continuous measurement scenario.
No, for the discrete case. I mean, the ability to predict, wouldn't it be less at later times? Because she has a shorter record. I mean, okay. I mean, it doesn't matter, is it?
In this scenario, I don't know how the prediction at later time thing comes in, but yeah.
It's not a prediction. It's a counterfactual inference. So it's not saying about what she will observe if she measures something different next time. It's saying, if in this run I had measured something in a different basis, what would I have probably seen? Yeah, so it's a purely philosophical question. What would I probably have seen? Yes.
And but if she didn't have the record, then I thought she had she gains. What does this mean? She gains 9.
So this is the amount of information that she gets if because she is conditioning on what actually she has measured, like her outcome. Like compared to if she does not use this information. Yeah.
Any other questions? If not, let's thank Ingita again.
Thank you.